So the next part, kind of an interesting, let's throw some stoichiometry in here just for fun. Further experiment, excess of hydrogen cyanide reacted with 17.4 grams of propanone, so an excess of this. 17.4 grams of that, and we know the molar mass, to produce 18.6 grams of the 2-hydroxy-2-methyl propane nitrile right there, and give us the molar mass of that. What was the percent yield of this, which we're now abbreviating HMPN? Well, when we got 17.4 grams of propanone, first thing you always got to do is convert it to moles, which we do by dividing by the molar mass. Then we look at the reaction and we see that 1 propanone gives us 1 HMPN. So therefore the 0.3 moles of propanone should give us 0.3 moles of HMPN. Multiply that by 85.07, the molar mass, to get the expected grams of 25.5 grams of HMPN. Only got 18.6. Well, that's right. Percent yield is what you got. 18.6 over what you could have got, 25.5 times 100 to turn it into percent, or 73%. A nice little pop in for some stoichiometry to rip up the question. So same question, but now we're taking our HMPN here and we're dehydrating it to give ourselves the propene nitrile. So see, we've got a double bond kicking in there, and this compound can undergo the addition polymerization, giving poly 2-methyl propene nitrile, just determined to confuse as much as possible with these long words, aren't they? Write the formula at the repeating section of this polymer. So this is actually just like a bunch of the easy questions we did at the start. There is the HMPN. We dehydrate it, and now we get the alkene, otherwise known as 2-methyl propene nitrile. And now we want to turn this into a repeating unit. So as we said before, you just lose one of the double bonds, stick an extra bond on each carbon, and there you go. Which of course we can turn into the polymer by just putting the brackets with the little subscript N around it. One difference between condensation polymerization and addition polymerization. This is addition polymerization, in which we essentially redistribute electrons from a double bond, but we don't lose any atoms in any way. Condensation polymerization, you always lose a small molecule, often water, sometimes something like HCl, and so on. So another question that's got 3 bits that could have gone elsewhere, but it made just as much sense to keep them all together. So anyway, arachidonic acid, unsaturated fatty acid containing more than 1 double bond. Bromine water used to confirm fatty acid is unsaturated with sufficient bromine used to react all the double bonds. So this, of course, the bromine water test is just electrophilic addition of Br2 across a double bond. Give the color change expected. Well, bromine water is light brown, and as all the bromine reacts up, it becomes colorless. Now we have an empirical formulas to do. This could have been in the stoichiometry worksheet. It probably is in the stoichiometry worksheet, but I could also pop it in here just, to have you remembering certain things. So the way I like to do empirical formulas is I first will write out the percentages. Now this shows me that I don't have hydrogen, but I'm told the rest is hydrogen outside of these. Percents all have to add up to 100, so we just add these up, subtract it from 100, and we find that we have 3.42% H. Convert that to how many grams in 100 grams. Same numbers, just changing the units. Turn grams into moles by dividing by the molar mass, which is something always to do, and you get the ratio of the types of atoms here. Now this is a gross looking ratio, so we make it pretty by first of all dividing through by the smallest number here, 0.212, and see what happens. And we get 1014, 16.1. Well, as this is empirical, let us say that that is 16 between friends. So the empirical formula, 10 carbons, 16 hydrogens, 4 bromines, and an oxygen. Now state the number of carbon-carbon double bonds present in a molecule of arachidonic acid. In other words, that's before we added the bromine water to it. Okay, and explain how we reached our conclusion. Well, the first thing to do is to say, well, in our formula here, we got 4 bromine atoms. Okay, seeing as how each double bond reacts with 2 bromine atoms, that would imply 2 double bonds. But wait 1 minute. First of all, this is not the molecular formula. This is just an empirical formula, which is a ratio. We're told that the compound is a arachidonic acid, and acids have 2 oxygens. Thus, to have a formula for an actual acid, we have to multiply this by 2, C20H32Br8O2. So now it's not 4 bromines added, it was 8 bromines added, which corresponds to 4 double bonds. Another question that has lots of bits that could have been in different worksheets, but it made as much sense to keep all those bits together. So compound X, hydrocarbon, contains 85.6% carbon by mass, and the relative molecular mass in a range 50 to 60. So first of all, let's get the empirical formula of X. Well, we know it's 85.6% carbon. It's a hydrocarbon, so the rest must be hydrogen, or 14.4%. Turn those into grams per 100 grams of the substance, convert grams into moles, as we have done many times before in our lives, and then make this a nice ratio by dividing by the smaller number, 7.13, and we get 1 to 2. So the empirical formula is CH2. Now what that means is that, of course, the molecular formula is some whole number times CH2. So if the molecular formula was 1 CH2s, which of course can't exist, the mass, molar mass, would be 14. If it was C2H4, in other words, 2 of those, the mass would be 28. If it was C3H6, it would be 42. If it was C4H8, the mass would be 56. And we're told that the mass is between 50 and 60. Ergo, the molecular formula is C4H8. Now, the second bit of this, 11.2 grams of X decolorized exactly 32 grams of bromine in the absence of light. Further bromine was decolorized when the reaction mixture placed in direct sunlight. What can be deduced from the fact that 11.2 grams of X reacts with exactly 32 grams of bromine? Well, we know that X is C4H8. We know it has a molar mass of 56, so that tells us that we had 0.2 moles of X in the 11.2 grams. 32 divided by 160 is 0.2 moles of Br2. So in other words, 0.2 moles of X reacts with 0.2 moles of Br2. Notice all I've done is I've just done what I encourage you to do automatically anytime you see grams of a pure substance, divide it by the molar mass to get moles. So seeing as how 0.2 moles of X requires 0.2 moles of Br2, so 1 X requires 1 Br2, there's going to be 1 double bond in X. Type of reaction mechanism occurs when X reacts with bromine in the absence of light. There is alkene plus Br2. Br2 adds across the double bond. It's an addition reaction. And indeed, it is an electrophilic addition reaction because what's happening here is that the reagent attacking likes electrons, those pi electrons, in the double bond. So what's X? Well, what we know about X is it's C4H8 with 1 double bond. And so that could be 1 butene, it could be 2 butene, which can either be E or Z, or of course it could be the 2-methyl propene, which is one of those isomers that a lot of people forget at this stage. When we react with bromine in the absence of light, all we're doing is we're adding bromine across the double bond, so a bromine atom to each double bond carbon. So that one, that one, that one, and that one. Fairly straightforward. Hopefully you'll manage that one okay. Another nice long multi-part question, different parts of which we could have put in other worksheets, but it's a nice flowing question to do here. An organic chemist suggested the following method for producing compound M from cinnamaldehyde. This is cinnamaldehyde here. Suggests 2 reasons why the reaction of cinnamaldehyde with chlorine is unlikely to give only the compound shown and give the displayed formula of another possible product. Okay, well, here is our chlorine reaction, reacting here with a aromatic ring that of course you can chlorinate and a double bond there. Okay, so we could put another substitution instead of having the Cl at the 4 position. No reason it couldn't go on in the 2 position. And of course, we've also got the possibility of chlorine adding to the double bond in a manner analogous to bromine adding to the double bond that we've discussed several times. So therefore, we could have had this possibility here. And of course, all the other possibilities where you're not just adding the chlorine in one of these places, but two of them. So you could have the adding to the double bond with the chlorine there, a chlorine there, and so on, and so on, and so on. So now part 2, we're looking at the reaction when we got HCl added here. Okay, so the HCl is added to this double bond, and the product that's suggested is that the chlorine goes on the carbon next to the aromatic ring, so the benzylic carbon, if you like, and the hydrogen from the HCl goes on the carbon that's attached to the aldehyde. Okay, and of course, any of these additions without something weird like peroxides around is going to go via a carbocation mechanism. Okay, but there's two possible carbocations that you get, both of which are secondary carbocations. Okay, so if we think about here's this starting material for step 2. We can put the H plus onto this carbon, in other words, the carbon that's attached to the aldehyde, which would mean that the carbocation is on this benzylic carbon here, or no reason whatsoever why the hydrogen can't go on the benzylic carbon, leaving the H plus on this carbon that's the positive on the carbon attached to the aldehyde. Each of these carbocations are, as far as we know with our current level of knowledge, equally likely because they are both secondary carbocations. Now, of course, once you've made the carbocation intermediate, the next step is for the Cl minus to pop in. Well, if the Cl minus pops into this top one, then we get this expected product here, or this stated product here, I should say. See, the Cl has gone onto the carbon next to the aromatic ring. However, if we have this equally likely carbocation, then the chloride can pop onto this carbon, giving us this other possible product. Okay, so two products are based upon which carbocation is formed. Each carbocation, as far as we can tell, equally likely. So in other words, step 2 will just give us two products that have to be separated from each other. So last part of the question, explain why compound M made in this way from cinnamaldehyde has no effect on the plane of polarized light. Now, why on earth would they ask a question like this? Well, because when we look at the structure of compound M, this carbon here has got a benzene ring or an aromatic group attached to it, a hydrogen, a chlorine, and then this group that contains an aldehyde. In other words, it is a chiral or a stereogenic carbon. Okay, and a stereogenic carbon would have two different enantiomers, and if you have one enantiomer, it will rotate polarized light one direction, and if you have the other enantiomer, it will rotate it the other direction. So what this is saying essentially is explain why compound M, even though it's got a chiral carbon, so therefore could have enantiomers, doesn't affect plane of polarized light. And the only way that happens is if you've got both enantiomers present. Well, now let's go to the mechanism to think about this. This was the carbocation associated with stage 2 that is now going to have a chloride added to it, which at that point has made the chiral carbon. Okay, now that chloride can attack from the top, or it can attack from the bottom. Now what I've done here is I've sort of abbreviated a little bit. So instead of drawing out this big aromatic ring here, I've got the pH, and instead of this huge big aldehyde containing, I've just called that R. Okay, because as long as I'm consistent with the use, it doesn't affect the discussion here. Now let's go through again what happens. If the chloride comes in from this side, well then the phenol group gets bent down that way. The H is at the back and the R is at the front. Okay, if it comes from this way, you can see that we're pushing all the groups up in opposite ways. And if I put them like this, you can see that they are enantiomers of each other because they are mirror images that are non-superimposable. Okay, and of course, if you've got a combination, an even number, an equal amount of the two enantiomers, then their effect on polarized light cancels out and they have no effect. This would be called a racemic mixture. Another question that could really not appear in any other worksheet all by itself, and seeing as how it involves elimination reactions, might as well discuss it here. So we've got a hydroxybutanoic acid right there, exists as a carboxylic acid, that's the acid group, and an alcohol, that's the alcohol. The alcohol can undergo elimination reactions, so dehydration reaction, to make these two acids. So which of these acids exist as EZ isomers? Well, if we look first of all at but3-enoic acid, there's carbon 1, which is defined by the acid group, carbon 2, there's carbon 3 where the double bond starts, carbon 4. Carbon 4 only has hydrogens on it, so therefore there's no isomerism dependent upon which way around those are, because it doesn't matter which hydrogen is where, which pink hydrogen is top, which pink hydrogen is bottom. H, the blue H, is always on the same side as a pink hydrogen, and the acid group is always on the same side as a pink hydrogen. When we look at but2-enoic acid, however, right here, so acid carbon is carbon 1, there's carbon 2 for the start of the double bond. Then we'll see that carbon 2 has 2 groups on it, carbon 3 has 2 groups on it. So if I just leave the carbon 3 the same and change up the groups on carbon 4, you can see that this is a different molecule. Okay, so because there are 2 different substituents on each carbon, we have 2 different isomers. This one is the Z isomer, this is the E isomer, because hydrogen is the lower priority on each of these carbons, so the Z with the lower priority on the same side, higher priority on the same side too, of course, and here in the E, the higher priorities on opposite sides of the double bond, or you could say the lower priorities on opposite sides of the double bond. Scientists reported the yield was 89% of these, 4% of these, and 7% other stuff. What other information would a scientist need to know the experiment could be repeated? And the answer is, quite frankly, everything else. This doesn't tell you anything about doing the experiment. It just tells you what the scientist got at the end. So examples of things you might need to know: any other reagents you have to put in, any catalyst you need, amounts of the substances, what temperature you reacted at, how long you did the reaction for, and then how you separated out all those different products. Finally, again, a question that I could have put somewhere else, but I put it here. Grape skins contain resveratrol right there. Addition of hydrogen bromide, so that's why it's here, because this is a addition reaction, results in this compound whose formula is shown below. Why do we not add HBr to the aromatic rings? And the answer is because benzene compounds don't add unless there's really weird, peculiar systems, because of all the pi electrons. They're not localized like in a double bond, they're delocalized around the aromatic ring. And if we react up those pi electrons with something to do an addition reaction like we saw here, it would destroy the very stable delocalized ring. Displayed formula for a compound produced when aqueous bromine is added to resveratrol. So if we're adding aqueous bromine, obviously, of course, this adds across the double bonds. No problem at all. But then when you have phenols in here, which we have, the phenol really activates the benzene ring, making it very, very, very reactive to substitution. And of course, bromine will substitute with aromatic rings